So what we'll do today is discuss the Bayesian approach to learning, and this is the subject of chapter 18 in your text. It's in a sense a more general approach than maximum likelihood learning, which was discussed in chapter 17, in the sense that in this particular approach we can integrate additional information into the learning process, which is known as prior knowledge. This is in addition to data. So we're learning from both data and prior knowledge. You will see that the formulation of Bayesian learning is mathematically very appealing, and in fact subsumes the maximum likelihood approach, in the sense that we will see in a precise way that when there is no prior knowledge, or this prior knowledge is really kind of neutral, then you will end up getting the maximum likelihood approach as a special case. So it's pretty interesting. There will be one main result that we will show today about this approach from a mathematical point of view. But most of the discussion is going to be set up and framework, because the Bayesian approach to learning is maybe a little bit different than what people expect. As I said, we set up the problem as an inference problem. So a lot of what we're going to do today is formulation and having you really think about learning in a particular way. That's going to be the main insights from today. All right, so let's first get a sense of what we mean by prior knowledge. Which is this additional type of knowledge that we will invoke beyond data when we're doing learning. And this is our recurring example from last time. We have this network structure, variable representing whether an individual is health aware or not, and this is whether they smoke or not, and whether they exercise. And we have this particular data set that contains 5 cases or 5 examples, right? And this is a complete data set, right? So 3 variables, and in every example, we know the value of every variable. Now, one notion that will become very visible and will make it into a first-class citizen in the Bayesian approach to learning is this notion of a parameter set. You've seen it, but now we're going to explicate more the notation and give it this name. So if you look at this variable here, h, we will say that this is a parameter set for the variable h. It's basically the distribution over h, but now looked at as a vector of 2 parameters with their own notation. Now, if you look at this variable smokes, as we know, there are 2 distributions here in the CPT for this guy, one conditioned on h being true and the other conditioned on h being false. So we're going to refer to each one of these as a parameter set. So look at the notation, second row. Theta of big S given small h. Big S is the variable, right? And that's conditioned on this guy being true. So that's one particular parameter set. Again, see the notation. There are 2 components to this vector. Each component now is S, small s, and small s prime. So the probability that someone is smokes given that they're health aware, probability that someone does not smoke given that they're health aware. So in this network, we have 5 parameter sets, right? 2 parameter sets here, 2 parameter sets there, and this particular parameter set. Now, here's an example of prior knowledge. Really, prior knowledge will amount to something that we know about the values of these parameter sets. In this particular case, I have 5 of them, and I'm saying that this guy, I just know it, right? The distribution over S given a health-aware individual, I just know it. It's a 0.1, 0.9. And the same thing, the distribution over this guy, whether a person exercises or not, given that they're health-aware, also I'm saying I know it. It's 80%, 20%, right? But look at the other parameter set. We still have 3 of them. So this guy here, I'm saying it could be one of these 2, right? So I don't know what it is, but I'm actually making it precisely one of 2. And similarly for the other guys, all right? I'm saying that the other parameter sets, it's either this or that, either this or that. So in a sense, I'm injecting information here that tells me something about what the values of the parameters are. Okay, this is one type. We will kind of graduate in what we say about parameters until we get to the main thing that people use to convey information about parameter sets towards the very end. So we're going to be doing this in steps, but this is one of the simplest things you can say. Now, then how do I learn in this case? So I'm giving you the data set, and I'm giving you this kind of information. I'm saying, let's learn. Let's find the parameters. Okay. That's a central concept that we're going to use in Bayesian learning. I'm doing it now informally, but what we're going to do is we're going to take a couple of passes at it until we pin it down precisely, because that is the essence of what's happening from a semantics point of view. And we're going to call this a meta network. And the idea is, look what's going on. This is what we're going to call our base network. This is the health-aware smokes exercises. And the idea is that I have different slices of this that corresponds to the different examples in the data set that I've seen. And now look at the parameters. They are explicated as variables in the network. So these guys here represent the possible values of the unknown network parameters, where the CPTs of these variables will encode our prior knowledge about these parameters, right? So now you can put actually a distribution. So not only can you say, let me go back, not only can you say, well, it's either this or that, you can even say it's 30% this, 70% that, right? So we can put a distribution over the possible values of the parameters that's going to be encoded by the CPTs of these particular guys, okay? So again, we're going to come to this network in more detail, but roughly look what's going to happen. Your prior knowledge will appear as CPTs on these guys. And these guys tell you what are the possible values of the parameters and how likely is each possible value. And then we're going to take the data set itself and view it as evidence on a meta-network. So when you tell me, here's my data set, I have 5 examples, I'm going to have 5 of these slices. And I'm going to assert the data set as evidence on these and then compute posterior distributions over these guys. And that's going to be the basis of learning. That's roughly what it's going to be like. Okay, we're going to look at it in more detail. It's actually even more interesting and intriguing than this, but that's roughly the idea. Once we set this up, the computational component or the computational part of this is going to be just inference as you know it. That is, we're going to be formulating learning as an inference problem. But we just have to set up the right model, right? So tune in and let me tell you, this treatment that we're doing here is non-classical. You will rarely see this. Typically, when you do Bayesian learning, people will just throw the equations at you. You don't see this formulation that we're doing here, which will really give you the basis for how these equations are derived. They'll just say, if you're doing Bayesian learning, do this, do that. We're now really telling you the whole story from inside, from within, of what is the basis of all of this. Okay, so again, just to orient ourselves a little bit more into all of this. When we set up this meta-network, it will specify a distribution that we're going to notate by this to mean the meta-distribution. And really, what's going to happen in learning is doing this kind of computation. This is the data set. It's going to be evidence. And then I'm going to compute posteriors over the parameter set. And that's going to be our basis for inference, as you will see in a little bit. For example, look what you can do. You can go and say, all right, here's my meta-network. I got the data set. I'm going to assert it as evidence. I'm going to compute the posterior over these guys. Right? Look what you can do. You can say, what is the value of these parameter sets that ends up having the highest probability? Remember the map query on Bayesian networks? What was the map query? You pick some variables and you say, find me the instantiation of these variables that have the highest probability. You can do this while choosing these guys as your map variables. And if you do this, what are you doing? You're finding the parameters that are most likely given the data set. And those are called map estimates, by the way. Right? This is in contrast to maximum likelihood estimates. Okay, we're going to get to this later, but anybody can tell me what would be the maximum likelihood estimates in this language? So in this case, I'm finding the parameters that has a maximal probability given the data set. What were the maximum likelihood estimates? There were the ones that maximize the probability of the data. So in fact, you would be searching for the parameters that will maximize probability of D given these guys. That's what we did with maximum likelihood estimates, right? We were looking at the probability of the data set given those particular parameters. We will relate them at the end, map estimates and maximum likelihood estimates. But you can already see the beauty of this formulation. It's very expressive mathematically. We can say a lot of things with that. Again, we're just doing now intuitive run. We'll pin down these a little bit more. Okay, once more, look what you can do here. The Bayesian approach, this is pretty important, does not necessarily commit to a single value of network parameters. So when we did the maximum likelihood approach, we were after what? One particular estimates. I give you a network, I give you a data set, and I say, what are the parameter estimates? You bring them to see, here they are. Okay, in this approach, you really don't need to do that in the following sense. The Bayesian approach does not commit to a single value of network parameters as it can work with a distribution over the possible values of these parameters. Now that I can compute a distribution over these, that already allows me to do certain things without having to go and say, what are the specific parameter estimates? And look, here's the example. The Bayesian approach can compute the expected value of a given query with respect to the distribution over network parameters. For example, the expected probability of observing a person that both smokes and exercises can be computed as follows. Look at this. This is it. This is a very important equation. We're going to look at it from 3 different angles. Look what's going on here. This here is what? The meta distribution, correct? That's the meta network we set up. And that allows me to compute a posterior over the parameter estimates. So every parameter estimate you bring me, I tell you, this is the probability it has given this data set. Now, that PR here is, we're going to call it the base distribution. This is the small network, 3 variables, and that's the distribution, assuming that I use theta as the parameters, correct? Now, in the maximum likelihood approach, what did we do? We found this theta, we plugged it in and computed the probability that someone smokes and is health aware, and I gave you a number back, correct? Here I don't have to commit to one. What I can do is sum over all possible parameter estimates, plug each one in here, and compute the probability of S and E under that parameter estimate, and then weigh by the probability of that parameter estimate. See what's going on here? I can give you an answer back to the query of what is the probability that someone smokes and they're also exercise. I can do that without committing to a specific parameter estimate. I can average over all of them and weigh by their probability, where this probability is computed based on the data set. It's kind of an expectation. What we'll do mostly today is pin this down more precisely. We will show you a bunch of interesting equations about this quantity. Now, you look at it and you say, that looks pretty bad computationally. That's a big sum here. How can I do this practically? Okay, the good news is, if the data set is complete, that's not bad actually. In fact, we will write this identity in different ways. That's going to be the highlight of today. Okay, so here's the agenda for today. And part of this is for Tuesday. We will define the notion of a meta-network formally, just a little bit. That's the essence of doing all of the mathematics. And we will describe a particular class of meta-networks that's commonly used in Bayesian learning. Right? We will give you a standard type of a meta-network. The beauty of Bayesian learning is you could do more with it and build different type of meta-networks. And then we will do parameter estimation while assuming that each parameter has a finite number of possible values, which is like what we did today. Next time, we will do it when we assume that we have an infinite number, or what we call the continuous case, which is the more common one and the one you will see in textbooks. Typically, people jump into this immediately. And I can tell you right now, the difference between the discrete and continuous is, if you have a discrete, then your prior knowledge is simply a CPT. You put the discrete values and you put the distribution, right? If you do the continuous, you need the new type of ways to specify prior knowledge. It's going to be something called the Dirichlet distribution. Some of you may have heard of it, but I don't want to throw that into the mix yet because it really doesn't affect the essence of what's happening. Okay, meta network. Here's how it looks more generally. What we have here is, we're going to call this the base network, and I have 3 instances of the base network. 1, 2, 3. In this example, I'm including 1 variable for every parameter set. Remember, here we said we had 5 parameter sets. 1 for this guy, 2 for this guy, 2 for that guy. Now I'm putting them all in there as first-class citizens, right? Okay, I want you to stare at this for a little bit. What's happening here? How did I construct this? I made 3 copies of this. I'm going to assume here that the data set has 3 examples. But if you had 5 examples, you will do 2 more. Okay, and look what I'm doing. 1 variable for every parameter set, but now look at the edges. I have an edge from this guy to every h. Why? Because the idea is the distribution over the h variable depends on this guy. Now, look here. This is whether someone smokes. I know that that depends on whether they are health aware or not. But which of these 4 is it having as a parent? Only 2 of these guys, this and that. These are the 2 parameter sets for S. One conditioned on H, the other conditioned on H prime. So this guy has these as the parents. Same thing for this S2 and S3. And E3, E2, E1 all have these 2 guys. In principle, if you look at this, this says that S1 depends on 3 guys, correct? H1, this, and that. Question. If I tell you that H1 is true, that is talking about health-aware individual, does this really depend on both of these? No, it's going to depend on one of them. This, it will no longer depend. That edge here from this guy to S1 becomes superfluous, it goes away. This observation is critical. In fact, it will stand behind one of the main equations you're going to see in Bayesian learning. I'm going to show it to you later, and to prove it, we'll just invoke this observation, and the rest is math you already know. That has nothing to do with learning. It's basic stuff about inference. Another question about this network. These variables that represent the parameter sets, they're all roots. What do we know about the roots in a Bayesian network? They are independent. Okay, this is also going to be the reason behind some of the key things you're going to see in Bayesian learning. Now, I have another question for you. They are independent. In a Bayesian network, roots are independent. But do they remain independent given evidence in general? No. Okay. Now, hold off on that one, because you're right, but you'll see that in some specific case here, they will continue to be independent. And that also will stand behind something major that we're going to see. You're studying the pattern. I'm asking you questions about independence, models, inference. We're going to translate them all to things about learning. One last thing I want to say before we leave this slide. This is a standard kind of a meta network that people use. It doesn't have to be this way. For example, you may also know that some of these parameters are tied up in some way. They're not completely independent, even a priori. With this setup, how do you do that? You just build a more refined network, right? And that may lead to different results. So you could incorporate assumptions about learning through the model, through the meta network, all right? But we're going to stick to the simple type and give you what is known about it, because that's what's commonly used. So let's again once more go over this. It's important. We have the 2 notions of a network. We have the base network, just like we've seen in chapter 17, that's the simple network would be H, S, and E, and we have the meta network. We will use this theta to denote the set of all parameters in the base network, this guy, and call it the parameterization. Equivalently, theta would represent the collection of parameter sets in the meta network, right? So if you go in the meta network and collect a value for this, a value for this, 5 of these, paste them together, you will get this theta, which is what I will need to stick into the base network. And then we have the base distribution and the meta distribution. This is the notation for the base distribution, right? It will be based on a particular theta. And this is the notation for the meta distribution. Okay. Let's just say, now again, this is going to be the last iteration on these guys to pin it down. If I have a meta network, then the prior knowledge on the network parameters will be encoded by the CPTs of that meta network. For example, in this case, we assume that we have 2 values for this particular parameter set, right? Distribution on whether someone smokes or not, given that they're not health aware. And we said that they're equally likely. So the CPT would look like this. This is the variable, and these are the 2 possible values for it. And this is the distribution, right? 50-50, or it could be 30-70, and so on. Again, we could do this nice thing here because this is a discrete parameter set. If it is a continuous one, we can't do that. We need PDF. We'll get to that later, next time. Okay, then the CPT is now part of the input to the learning process, and this is a major distinction with the maximum likelihood approach, right? This particular input. Now, this we already did visually, but let's now look at it mathematically. We're trying to fully specify the meta network, right? So the CPTs, the structure of the meta network is now clear. I think people agreed that you can draw the structure. Should be no ambiguity. Now we want to pin it down. To pin it down, you need 2 types of CPTs. The CPTs over the parameter sets, which we just did, and then you need the other CPTs. The CPTs of other variables in the meta network, i.e. ones that do not correspond to parameter sets, are determined by the intended semantics of such networks. Again, we did this. You gave me the answer, but let's look at it as an equation. Consider a variable x in the base network that has this parents, u. In the meta network, we know that we're going to have a bunch of instances of this, right? x1 through xn, where n is the number of examples in the data set, and similarly, we're going to duplicate the parents, right? Okay, now, when we look at the CPT for a particular xi, right? When we look at the CPT for a particular xi, now it's going to be conditioned on what? On a particular value of its parents and these parameter sets. Correct? What did we say? Only one of these guys will be relevant to X. Correct? The guy that's conditioned on that same value. So look what's going on here. This whole thing is this. Where? Da. You already told me this when we looked at it visually. What this is saying as an equation, and here's a concrete example. I'm looking at the CPT for smoke, whether someone smokes or not, given that they're health aware. These are the 2 parameter sets. But actually, because they're health aware, it's this guy that's relevant. The distribution over smokes is just that guy. And now that they're not health aware, it's this guy that's relevant. You guys see it? Very intuitive, very simple. You can easily synthesize the meta network. Once I give you the base network and I tell you how many examples I have, and the only thing you need is just the priors over the parameter set, and you're basically set. Okay, now this is the last bit of visualization. In this case, we assume that we had 3 examples, 1, 2, and 3, right? This is the data set. Now, we kept saying data evidence. Well, that's what we mean. The data set can be viewed as the following variable instantiation. So when I do this, I'm looking at it. H1 is this, S1 is that, E1. So this first row or first example is this. Second example that, the third example is that, right? And now That is evidence now as we know it. It's a variable instantiation. All right, folks. So I think notationally and semantically we have pinned this down now nicely. Now let's start to make observations about what's going on. Here's the first thing, and you already answered this to me. We initially have the following distribution on parameter sets, right? This is the meta distribution, and this is all 5 parameter sets, and I'm looking at the prior on those. We already agreed that since these are independent, look what we have. We have this, correct? So if I tell you compute the prior on a complete parameterization, you can take the prior on each parameter set and take the product, right? You know this immediately from what you know about Bayesian networks by looking at the meta-network structure and realizing that the parameter sets are roots. Now, here's the surprise, perhaps. This decomposition still holds, even for the posterior, given that the data set is complete. If this data set is complete, then you can also write this as the following. So the posterior decomposes under complete data set. Now, what does a complete data set mean? Right? Let's go back to the previous guy. What does that mean? That means in every row, I know the value of every variable, correct? On the network, what does it mean on this picture? That means I know the value of all of these variables. Right? 3, 3, and 3, all observed. You guys see that? Now, what we're going to see now, how is it, why is it when I know the value of these, all of them, I still have deseparation? These guys will be deseparated or will be independent in that case. I'm going to show it to you next. Okay, you need to look at this, stare at it. On this side is the meta-network. And look what we did. I have a data set with 3 examples. I showed it to you before. And on this side, instead of, in every variable, I put the actual value. So H, this is big H1, that's the variable. In this case, what did I put? Small h. That was the value of this variable in the first example. And here was S prime, not a smoker. So the first example was a health-aware individual who's not a smoker and who exercises. And the second example was health-aware, does not smoke, does not exercise. And the third example was not health-aware, smokes, and does not exercise. Okay, so in this picture, I put the actual values. This is the original meta-network. And now that I know the value of each one of these, look what I did. I pruned it. To prune this network, you know what pruning is. Pruning is when I go and simplify the network, but I guarantee you that you're going to still get the same answer. What I'm trying to do here is compute the posterior. That's the query I'm interested in. I'm interested in computing the posterior over these parameter sets. Right? Given the evidence, that's what we're after. And the claim is, here's the evidence, and I removed edges, and I'm claiming that if you compute the posteriors over these guys with this guy, you're going to get the same thing here. What did I do to prune? There is the technique that you know from early. If I know the value of a variable, what can I prune? Edges out, going from that variable, correct? That explains what? That explains the fact that I killed the edges coming out of the h's. So this h has 2 edges coming out of it, they're gone. Correct? Similarly for this, because I know the value of these, and of course we adjust the CPTs for these. Fine. That does not explain every edge that was removed in this case. Correct? There were more edges removed, not by this principle, but by another principle, which you discovered just like 10 minutes ago. Remember what that is? Look at this guy, S1. How many edges going into S1? 3 from H and 2 parameter sets. What did we say about these 2 parameter sets? One of them is relevant when H is true. The other is relevant when H is false. When the value of this is true, then this guy depends on this parameter set. And this is no longer relevant. Second guy, correct? That is the second reason, or the second principle for pruning edges. Look at this guy here. What is the value of H? True, health aware, correct? In that case, this is no longer relevant. We can delete that edge that goes from this guy to S, and that's what's happened here. It's been removed. This is probably the most important picture today, in the sense that if you know it and you invoke what you know from before, you can pretty much derive other things. That is the main insight. Of course, it assumes that you already understand what a meta-network is. So understanding a meta-network together with the fact that I have a complete data set and that it leads to this kind of pruning, the rest is just you have to be relaxed with a pen on paper, and then you'll sit there and derive the other things. Any questions on this? Because now I'm going to ask you a question. There's one more thing about this guy. Okay. Stare at B. B has actually a very interesting structure here. That's going to be the secret of the equation for computing posteriors on, because the end result today will be, I want to show you, well, there's two technical things we're going to say. One is a formula, a closed form for computing the posterior on each parameter set. I need that, because that's going to be the basis of doing various things. But look at this. What do you see? Okay, I'll help you with it. What is this guy? You've seen this structure before? Naive Bayes. Naive Bayes. This is a naive Bayes structure. You've got the parameter set. I have a prior on it. I'm trying to compute the posterior, and I have a naive Bayes structure. The nice thing about naive Bayes structure has a very nice closed form. Okay, this guy is naive Bayes. Correct? Look at this guy. What is this guy? It's a funny looking naive Bayes. It's just inverted. This is naive Bayes too, right? What about this guy? Naive Bayes, naive Bayes. Okay, all of them are going to be naive Bayes. In fact, if you take the meta-network and assume that the data is complete and do the pruning as we discussed, what you're going to get is a bunch of disconnected naive Bayes networks where the root of each is one of your parameter sets. And now I hope you can see why this will allow you to have nice closed forms for the posteriors. I'm going to show it to you. Okay, I think this is a good time to do the break. What we'll do when we come back is basically start seeing the benefit of all of this. And it's really going to boil down to a couple of equations that allows us to obtain answers from Bayesian learning and contrast them to the answers that we get from a maximum likelihood. So let's take our 10-minute break.